Okay, for this video, I'm coming to you from a super secret undisclosed location. Might be able to make a few videos here. Usually I'm at the school, but right now I'm not. So it's no big deal. I'm in a nice quiet place. It's not my house, otherwise it wouldn't be nice and quiet. But it looks like a house. It is a house. Okay. This video, I'm going to, we did some dividing polynomials in the last video. Well, we can still think of that. If I just divided, some b to the power of 5 over b to the power of 3, we subtract those exponents and we get b to the power of 2, right? Okay, no problem. Well, what if I went the other way around here? What if it was b to the power of 3 over b to the power of 5? Well, I subtract the exponents and I get b to the negative 2. Okay, b to the negative 2. Well, what are we saying here? B cubed means I've got b times b times b, and b to the 5th means I've got 5 of those b's down there, right? And if I start canceling common factors, all of a sudden I 1, 2, 3, 4, 5. All of a sudden I run out of stuff on top, which means there's always a times 1 there. So it's 1 over b squared. Okay. Well, what is 1 over b squared? It's the same thing as b to the negative 2 power. Okay, those two things are the same. They don't look the same, but they are. All right, so it's two different ways to look at the same thing. You can think of every number as a fraction. Okay, you can think of that as b to the negative 2 over 1 or 1 over b to the positive 2. You can always think of a number as a fraction. And the difference between the positive exponent and the negative exponent is just the position within the fraction. So in other words, a b to the positive 2 in the denominator is the same as a b to the negative 2 in the numerator. This is dealing strictly with monomials, single term up top, single term on the bottom. Okay, so that's what we'll do here when we do some of these divisions. But we're always, part of our simplification process is always going to be to clear those negative exponents out of there. But let's just practice the rule here. So if I have 7 to the negative 2, I can think of that as a fraction over 1. It's 1 over 7 to the positive 2. Okay, if I have whatever it is, 4 to the negative 3, it's 1 over 4 to the positive 3. Okay, if I've got 1 over 2 to the negative 4, oops, I'm running out of room. I'm going to move that now denominator to the top, 2 to the positive 4. Yeah, I could say over 1 if I want, but you don't have to show a denominator of 1, okay? You would have to show a numerator of 1. All right, so that's kind of our rule here. It follows along with this rule of division. I'm going to subtract exponents, but maybe I'm going to get a negative exponent. If that happens, hey, it happens. We can clear the negative exponent out by moving it to the other part of the fraction. So if I have 4 to the negative 3 over 5 to the negative 2. I'm just going to switch both of these now. It'll be 5 squared over 4 cubed. Okay, and then of course I can finish it off. Call it 25 over 64. Okay. If I have something in parentheses raised to a negative exponent, that's okay. It's just 3 to the negative 2 over 4 to the negative 2, which means it's really 4 to the positive 2 on the top, 3 to the positive 2 on the bottom, or 16 over 9. Okay. X to the negative 5th over y to the negative 1. Y moves. You don't have to write a positive 1 if you don't want to. X to the 5th goes down. Okay. How about 1 over 4x to the negative 3rd? Now, in this case, the 4 is going nowhere. Okay. Only the x to the negative 3rd is going to move up and become x to the positive 3rd over 4. Okay. All right, so that's going to always be a requirement, as we work these problems. If I've got 2 to the negative 3 over 2 to the negative 4, I'm dividing, which means I'm subtracting. So it's 2 to the negative 3 minus negative 4. Remember, subtract, which is really 2 to the negative 3 plus 4, or just 2 to the 1, or just 2. Okay, all good there? All right, so to kind of review and recap all these things we've talked about in these last few videos, if I have some b to the m times b to the n. It's b to the m plus n. You add the exponents together, same base, okay? What if I'm dividing? B to the m over b to the n. Well, now I'm subtracting b to the m minus n, okay? Product rule, products to powers. If I have some a, b all to the power m, that's a to the m, b to the m. Okay, similarly with a quotient, a division, that's a to the m over b to the m. Okay, how about an exponent raised to another exponent? B to the power of m and then raised to the power of n. Well, that's b to the m times n. That's when you multiply the exponents. Okay, and then finally b to some negative n is 1 over b to the positive n. Okay, that's a nice little recap of all these things we've been kind of dealing with. And now let's use them a little bit more, practice these negative exponents. Then we're going to talk about a thing called scientific notation. X to the 4th over x to the 20th. I'm going to subtract and get x to the negative 16th. And then I'm going to clear that negative exponent out, and I'm going to call that 1 over x to the positive 16th. Okay, 10y to the 7th over negative 2y to the 10th. Well, the 10 and the negative 2, the coefficients, that's regular division, negative 5. Y to the 7th divided by y to the 10th, I'm going to get y to the negative 3rd when I do that. Negative 5 is not going anywhere. Y is going for a ride downstairs. So it's negative 5 over y to the 3rd power. Okay. How about x to the negative 9th times x to the 4th? Well, here I'm going to add the exponents. So now I'm going to add the negative 9 plus 4, which is x to the negative 5, which is 1 over x to the positive 5. Okay, I like it. What about this one? What about x to the 5th over x squared, all raised to the negative 3 power? Well, let's do this division first. X to the 5th divided by x squared is x cubed, and then that x cubed was being raised to the negative 3rd power, which makes it x to the negative 9th, which means 1 over x to the positive 9th. All right, I like it. Everybody cool with those exponents? All right, we're going to talk about a thing here now called scientific notation. Scientific notation is a way for us to represent very, very large and very, very small numbers. Okay, the format is you're going to have one digit. I'll just use numbers instead of trying to put it generically. One digit, so 5, and then your decimal point, and then 1 or 2 more. We'll round it off some more. 5.12, but then we're going to multiply by 10 to some power. In this case, I'll just say the power of 6. This is the scientific notation form of this number, which if I wrote it in what we call standard form, I'm going to perform this multiplication, which means I got to move that decimal 6 places to the right. So it would be 5120000. It would be 5,120,000. Okay, this would be standard notation. Okay, scientific notation is a more shorthand way to do it if you have really large numbers. Like let's say I have 8, 4, 3, 2, 6, 9, 4, 1, 0, 8, comma 2, 4.3. Okay, I got this big old number. Well, I don't need to know every little thing here. I just need an idea. How big is this number? So the scientific notation says, all right, grab your decimal wherever it is and put it right there. So it's going to be 8 point, round it off now, 43, 43, whatever. Pick your round off point. 8.43 times 10 to some exponent. Well, how many places did I move that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 places. Times 10 to the 11th. Okay, the scientific notation way to write that number. Now, if you ask me to go here and expand it back out now, though, what's going to happen? I'm just going to move that decimal 11 places, right? First 2 places gets me past the 3. Now I need 9 zeros. Okay, now you'll notice I've lost some precision to that number, and I've also done something here. What have I done here? 1, 2, 3, 4, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, it's 4, 3, 2. Let's just pretend that one never happened. It's what am I trying to say? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 places. 4, 3 with a 9, 0. What did I do wrong here? Oh, I'll tell you what I did wrong. My commas are screwed up to begin with. Ah, you know what? Pardon me. Okay, the number should have been 843, 26. All right, I quit. I'm sorry. I don't want to start over. Let's pretend that problem never happened. Bear with me. I'm sorry. Let me just write it over. 8, 4, 3, 2, 6, 9, 4, 1, 0, 8, 2, 4.3 is what I had there. So I tried to go back and put my commas in so I could read it, properly. Okay, there we go. That's what I had. And I said, okay, scientific notation says I'm going to leave the 8 decimal point, carry 1 or 2 more digits, and then times 10 to some power. Well, the power is how many steps to get from there to there. And we said it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We said it's 11, right? Okay. And then I said, okay, that's standard scientific notation. If you want to go back to standard, you're going to multiply this out. And you're going to get 843 with 9 zeros after it. Okay, so you notice I've lost some precision to my number, right? Because now I just have this number here. I've lost all this little precision here. Maybe that precision is important. If it is, then scientific notation is not the way to go. Maybe it's not. Maybe you just want an order of magnitude. What are we talking about here? How big is this number? I don't care about the little chump change numbers down here. I want to know the big number. Scientific notation lets us represent that big number in a more convenient form than writing it out in standard notation. Okay, so that's large numbers. What about small numbers? What if I had, 8.21 times 10 to some negative exponent, like a -5 here? Well, we learned a second ago, negative exponent's like 1 over a positive exponent. So this would be like saying times 1 over 10 to the positive 5, right? When we talk about our rules of exponents. Okay, now this is the same thing as saying a fraction times a fraction. 8.21 divided by 10 to the 5. 10 to the 5 is a 1 with 5 zeros. I'm dividing that 8.21 by a bunch of powers of 10, right? So what would it be? It's going to shift that decimal 5 places to the left. So I'm going to have 4 leading zeros and then an 821 if I perform that calculation. Well, all I did here is I look at my -5 and I say, aha, 1, 2, 3, 4, 5, and I fill those in with zeros. Okay, so a very, very small number can also be represented by scientific notation in this fashion. Okay, so let's give ourselves another one here. What if we have 1.1 times 10 to the -4th power and we want to go into standard notation? I'm going to move that decimal 4 places to the left. So 1 place gets me there. I need 3 leading zeros. So my decimal point, 3 leading zeros, and then a 1, 1. That's the same thing as this. Okay. So what if I want to go the other way? 0.0000000000024. Woo! I'm going to change it such that I have one number, one non-zero number, and then a decimal point. So it's going to be 2.4 times 10 to some exponent. Well, what's the exponent going to be? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, -11 in this case. Okay. And that's how we would do that. Okay, scientific notation always has 1 digit and then the decimal point, and then you can carry 1 or 2 more digits after that, times 10 to some power. If it's a positive power, it's a big number. If it's a negative power, it's a small number. Okay, gives you an order of magnitude. So let's talk about a couple of everyday big numbers we might want to think about in the world. Actually, we might not want to think about this in the world. Our current national debt, If you go to usdebtflac.org, it tells you all kinds of government expenses. Here's our current national debt. Oh, come on now, baby. Zoom in. Let me put it down and zoom in. Maybe that'll work. There we go. 27,892,123,000, blah, 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 blah. It's increasing, I don't know, $30,000, $40,000 a second, I'm going to guess. Okay. That's a big number. That's a number we might want to write in scientific notation, right? So it's 27,892,124,000,000. I can't even see the rest. It's changing so fast, right? Let's say $382,437. Let me zoom back out of here. And 23 cents. Okay, that was the national debt at one point in time. Let's put that in scientific notation, shall we? We'll call it 2.7, round that 8 up to a 9, 2.79 times 10 to some exponent. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13th power. Okay. All right, that is a little thing on scientific notation. Let's do one more thing, which is kind of fun, and it also helps us with something we're going to do on unit conversions. All right, so what's going to happen now with our calculator when we deal with a really big number? How does our calculator show it in scientific notation? So let's talk about a really big number. If I wanted to calculate the distance across the entire universe, okay, what we call the observable universe, how many miles across is it? That's got to be a big number, right? So we need to know a little bit of info about it. We need to know, one thing I looked up is that the distance across the observable universe is 93 billion light years. Okay, now light year is not a measurement of time, it's a measurement of distance. How far does light travel in 1 year? That's a distance. Well, if I knew that distance and I multiply by 93 billion, that's going to be the distance light travels in 93 billion years. And that's how big this universe is that we know of. Okay, so we need to know a little bit of information to do this calculation. It's just kind of fun because it lets us practice unit canceling, which I'm going to focus on more in another video, but it gives us a big number in our calculator too. So we need to know one more piece of information. We need to know the speed of light. Okay, and if you don't know, it's 186,000 miles per second. Okay, I'll say 1 second. 186,000 miles, boom, 1 second. That's how fast light is. And even at that ridiculous speed, it takes 93 billion years to go all the way across the universe. It's that big. It's just mind-boggling. So how can we do this calculation? I want to know how many miles that is, and not how many light years. I want to know how many miles. Yeah, there's a conversion from light years to miles, but that takes all the fun out of it. Let's do it ourselves. I'm going to turn this pad around to give me a little more room. If I take 186,000 miles per second, okay, well, that's 1 second. I know there's 60 seconds in a minute, right? So if I multiply by 60, my units of second cancel. And we'll talk more about this in a future video. I'm going to be left with miles per minute. Okay. Well, I know there's 60 minutes in an hour, right? 60 minutes per hour. So now the units of minutes cancel. And if I multiply by 60 again, I'm going to have miles per hour. I know there's 24 hours a day. Hours cancel, and if I multiply by 24, it's going to tell me how many miles light can travel in 1 day. Let's forget about leap year, keep it simple. We'll call it 365 days in a year. The days will cancel, and if I multiply by 365, I now know how many miles light travels in 1 year. Well, now I'm going to multiply that by 93 billion years. Okay, so think of that as being off to the side there. Years are up here in the numerator. It's going to cancel off years down there in the denominator. And the only unit left on the board is miles. That's what I'm looking for. How many miles? All right. What's going to happen to our little calculator? It's going to explode, I think. 186,000. Let me just see something first. Yeah, see, some calculators are going to have limited screen space. Okay. This one does, others don't. So if you don't have enough room to even put the biggest number in there, like our 93 billion, we can just break it up and we can call it 93, thousand times 1 million. That'll be the same thing. So I'm going to have to break that up into two pieces when we get there. All right, 186,000 times 60 times 60 again times 24 times 365 times 93,000 times 1 million equals 5.46 if I round it off. And you see over here in the corner, there's a little 23 kind of tucked up there in the corner. That means 5.46 times 10 to the 23rd power. Okay. Miles. Okay, that's how far across the observable universe is. That's what our calculator does when we try to put a scientific notation, a big number in there. It reverts the scientific notation because there's not enough room on the screen to show everything. Okay, so that was, again, fun little example. I don't expect you to recreate that or anything, of course, but it does show unit canceling, which we'll get to more also. If you're asked to do a calculation in scientific notation, which I don't recall any on the exam, to be honest with you, but just in case, if we were asked to do something like 4 times 10 to the 5th times 2 times 10 to the 9th, let's say. Well, it's very similar. It's, very similar. If I asked you to do, I'll go down here, 4x to the 5th times 2x to the 9th, I hope you would tell me it's going to be 8. X to the 9 plus 5 is going to be 14, right? Well, same idea. It's going to be 8 times 10 to the 14th. All right, no big deal, right? Now, what if my number of 8 was bigger than 10, though? What if it was 6 times 10 to the 3rd power times 5 times 10 to the 4th power? Well, 6 times 5 gives me 30 times 10 to the 7th power. But remember, scientific notation only wants one digit and then the decimal point. So that 30 is like its own little scientific notation of 3 times 10 to the 1st power, right? Then we have times 10 to the 7th power. So it's 3 times 10 to the 8th power. So I need to shave an exponent, a power of 10 off of my 30 there and put it over here with the 10 to the 7th to make it 10 to the 8th. Let's try one more like that. I don't think I explained that well enough. 6 times 10 to the 5th times 7 times 10 to the 4th. 6 times 7 is 42. 10 to the 5th times 10 to the 4th is 10 to the 9th. Okay, but if I just said write 42 in scientific notation for me, please, you would have to say it's 4.2 times 10 to the times 10 or 10 to the 1. So I have to do that, and that 10 to the 1 is going to go with 10 to the 9th to make it 10 to the 10th. Okay, divide, same idea. If I have to divide 6 times 10 to the 5th, divided by 2 times 10 to the 3rd. Well, 6 divided by 2 is 3, and then I subtract the exponents here, times 10 to the 2nd power. Okay, all good there. How about 1.2 times 10 to the 6th over 4.8 times 10 to the -3rd. Now we got all kinds of little things in here. Well, first of all, 1.2 divided by 4.8 is going to be a number smaller than 1. We'll have to deal with that in a second. 0.25 times 10. Now I'm going to have, remember what it is. It's going to be 10 to the 6th minus -3. minus negative is really plus positive, so it's really times 10 to the 9th. Okay, however, this is not proper. I have to have one digit and then my decimal point. So that's really got to be 2.5 times 10. I'm going to have to shave off a number to the 8th. Okay, so I don't know if you'll get too many of those, if any, to be honest, on the exam, but that's how you would deal with, problems involving multiplying or dividing scientific notation numbers. Okay. All right, we will leave it at that for this video. We're going to start talking about some factoring and more polynomial stuff here in the next one.